Zoom recording. All right. Hopefully you guys are able to see my screen. It should look similar to the kind of screen that I've used at different times with you guys in class using my smartboard. Essentially what I did is turned my laptop into a smartboard. So hopefully you guys are able to see what I'm writing. If you can't, like if you do not see on your screen right now, it should say COVID-19 lesson. You do not see that, please put in the chat, like I don't see what you're talking about, Miss Ankala. And I'll try and troubleshoot it. Even if that just means that you guys are just gonna have to listen to me talk for now until I'm able to record it. Ethan, I don't know if this will help answer that question, but probably not. I mean, at some point, I mean, from a like long-term point, yes, but like immediately, I don't know, probably not. So first things first, I'm going to start by reviewing the exponential function equation because it's probably been a while since you guys have looked at that, unless you did your Khan Academy assignment already, which you technically should have. But our exponential function equation has been f of x equals a times b to the x power. That's the equation we've been kind of using. It's like some variation of this equation. So in this equation, a has always been our initial value or our initial amount. And then b has been our rate. So what I want to do today is I want to kind of talk about the COVID-19 virus from a math perspective, because there's a lot of different perspectives that we can talk about what's going on. We can talk about it from a government perspective. We can talk about it from a historical perspective. We can talk about it from a scientific perspective. So I want to talk about it from a mathematical perspective, which shouldn't be shocking to you guys that that's the way that I think about things. And specifically what I want to focus on is this graph right here. I saw it going around on social media, and I saw it going around on like Instagram, on Facebook, on Twitter. It was going around everywhere. And it seems like a lot of people, if you guys were following my Instagram, I posted a little joke about it, but a lot of people have been looking at exponential growth functions lately, but haven't really understood what they meant or how it looked or what all those things are interpreted as. And so I kind of wanted to talk about the actual equation for the exponential growth of the virus right now and what social distancing can do to help alleviate that, and like what mathematically is the difference between the red graph there and the blue graph. Okay, so let's start, and again, keeping in mind this equation, I want to kind of start looking at the rate of infectivity based on the United States. So I'm going to be bouncing back and forth between different websites because I wanted to pull like the most recent data, and also like because sometimes their graphs are better than mine and there's no point in making something just to say that you made it. So I wanted to look here. Okay. So here's a graph of the cases of the COVID-19 virus in the United States. There's a couple things that I want to get from this. So first is the first recorded date on here is February 15th, and that had an initial number of cases of 15. So we have our initial value. Our initial value is 15 cases. When we talk about infectivity, when we talk about the rate of infectivity, usually we talk about it in terms of how often something doubles, which I had it pulled up somewhere here, but I don't remember where. But it said on here, oh, I can't find it. You're just gonna take my word for it for now. But on average in the United States, the number of cases is doubling every 5 days. Sorry, Victoria, I got distracted and didn't see that you popped in. Based on the most current numbers that I checked this morning, the number of cases are doubling every 5 days. So let's think about that in terms of a rate, right? So doubling, let's think about, so I'm gonna write this so that we can visualize. So doubles, and this is based on US numbers. And I'll send you guys, when I share this with you guys, I can send you guys the links if you want to do your own research or if you want to fact check me, which I totally invite. but it doubles every 5 days. And I want to take that doubles every 5 days and I want to turn it into a daily percentage of increase, okay? So doubling, let's start with that actually means. We've talked about doubling, and a lot of times we think of it as multiplying something by 2. Really, what doubling means is an increase of 100%. Oops, not 10%. 100% increase. So doubles means it's 100% increase. So that means we have a 100% increase happening every 5 days. So that 100% increase needs to be split up over 5 days so I can find what our daily rate of increase is. Okay, with me, kind of, sort of. So 100 divided by 5, if you're like quick with your math facts like some of you guys are, we know that this is 20, which means we have a 20% increase in cases each day. And this is just based on current rates, like I said. I'm not saying that this is perfect, this is just based on what I found. So we're increasing by 20% every day. Well, an increase of 20% means our actual rate is 1.2, right? Because we remember like an increase of 20% means 120%, right? Because we're increasing our cases. So that means our rate is 1.2. So our equation for the actual growth is f of x equals our initial amount times 1.2 to the power of the number of days it's been since, what was it on there? Was it March 15th or was it February 15th? I'm pulling it back up. I was planning on pulling it back up. February 15th. So we could use this equation, because right now, if you look, this is not a math graph. This is the actual graph of the number of cases. But it looks exactly like an exponential growth equation, right? This should look a lot like what we were doing in class. And that's just the way viruses work. In fact, exponential growth, one of the first times it was ever observed was in the terms of a virus. So it's following this. Now, based on what we know, it's doubling every 5 days. So let's check and see if that's accurate. So if I look at this day, so I'm gonna look at February 15th, jump ahead to February 20th, no, but if I look at February 21st, yes. We went from 15 cases to 35 cases. Jump forward another 5 days, and we went from 35 to 60. So as we can see, like we can follow this graph and see that every 5 days it is in fact doubling, or every day is theoretically being multiplied by 1.2. Now, the reason that doesn't always reflect in the graph is it depends on how often people are being tested and how often it's reported. But that is what we're dealing with right now. This is the case that we are following at the moment, okay? But as you guys know, we have started officially social distancing and sheltering in place and doing all of that. So I want to talk about how that choice of social distancing and staying home and not going out is going to impact this equation. Because again, I think of everything from a math perspective. So because I found this visualization of how the virus actually spreads. So this is also just a cool little GIF of the flattening the curve. Is the concept of a super spreader. So if you look here, people in red in this GIF are infected, and you can see that as they're in contact with all the other blue dots, they're infecting the blue dots and making them red. So I want you guys to see how like it's spreading, and it spreads from these small points, and then it goes to these big circles. These big circles are what's considered super spreaders. So an example of super spreading situations are for like schools. I mean, how many people do you come in contact with at school, between your bus, between the gym, between the cafeteria? I mean, going from class to class, like you might not directly talk to all 100 students that I have, but you're certainly sitting in a room that had over 100 people in it. So those types of places were the first types of places we wanted to kind of limit contact with. By cutting out some of those super spreaders, we are able to change that to something that looks a little bit more like that. Okay, which I know these graphs are kind of crazy and kind of hard to follow, but we're essentially trying to cut out these big circles. Now, what that does is what it effectively does is it doesn't necessarily influence the doubling. It's still going to double. The number of cases is still going to continue to double. What we can change is how many days it takes to double. So with social distancing, we're able to make it, instead of doubling, which again we said was 100% increase, over 5 days, we're able to change it to doubling over 10 days, okay? So if I'm able to change that to doubling every 10 days, that means we only have a 10% increase per day. Now to clarify, even though we're social distancing, even though we're staying at home, we're still gonna see more cases of it. We're still gonna see more people being infected, but at a lower rate. So we can't change the initial number of infected. That's not something that we're able to change at this point. But now, instead of having 1.2 as our rate is 1.1. And that's still being raised to the x power. Now I know some of you guys out there might be thinking like, well, that's such a small change. Like that's such a minor change. But think about how many equations and stuff we did in class where there's a huge difference between a 10% increase and a 20% increase. I mean, if you even think of your car buying project, the change in interest rate had a huge impact on how much you were paying overall for your car. So even though this isn't a huge change in terms of the actual number, it's going to have a huge impact of how quickly that infection is spreading. So if I were to look back over here, the other thing I wanted to point out to you guys is the other part of social distancing and the other part of trying to stop the spread. So if I'm looking at the without protective measures of this graph, the red part, that means we are effectively having cases for a shorter period of time. With the social distancing, we're going to have cases for a longer period of time, but less at a specific time. So this is how much our hospitals are able to help. So like we only have so many respirators, we only have so many ventilators. We're trying to keep the total number of affected below that number, right? So like if we were going to say that there were a total of, I'm just gonna throw out a random number here because again, I'm a numbers person. If let's say we have a total of 200,000 respirators. Ooh, that's not how you spell that word. And this is just an example, not real data. I'm just making this number up. Then that means in theory, we want to have less than 200,000 people at a time infected so that we're able to treat them. So that means that we might be dealing with the virus for a longer period of time, but less at a time that are exactly infected. Now, the other thing I wanted to talk to you about, which is kind of related to Ethan's question that he asked at the beginning, believe it or not, is this point. Okay, this is probably the point that you're focusing on, the point where it levels off and then it starts to go back down. Exponential growth can only describe the spread of a virus up to this point, where it changes from exponential growth and then it starts to do the opposite. It starts to level out for a little bit until eventually it goes on an exponential decay. There's a couple of reasons for that. One is exponential growth implies that there's an infinite number of people. Well, there's not. The other part of the exponential growth function and like trying to represent a virus with exponential growth is that it implies that people can keep getting infected over and over again. And right now that doesn't seem to be the case. Once you've been infected, you've done it, you've gotten over it, you're not sick anymore, but you also won't get reinfected. So that means the odds of an infected person coming in contact with a non-infected person who's never been infected are going to continue to decrease. This is also taking into account the fact that they're going to get treatment. There's going to be cures, there's going to be vaccines, all those things will eventually happen. And therefore we're going to see an exponential decay, an exponential decline of people who are infected. But right now we are in the scariest portion of that graph, okay? We are in the part of that graph that makes it seem like it's just going to keep going up. But every disease that has ever happened has followed this type of a curve, okay? We're just in the scary piece of that graph, okay? In terms of when we will hit that point, like the actual day, I do not know. But I do have a really good video that describes when we will get there from a math point. Like, when will we know that we're at that point? And there is a specific mathematical way to know. And it's in this video, which I'm also going to share with you guys on Google Classroom. Even if you've tuned in to watch this with me live, I would still recommend watching this video on your own time, especially if you feel like you are freaking out or you want to know more about the math behind this type of thing. It's going to talk to you guys about a logistic curve. And I originally thought about just sending this video to you guys and not having me talk at you, because I know that I'm talking quickly and I feel like I'm talking at you instead of talking with you guys. But the video was talking about things on almost a calculus level of math, and I wanted to kind of bring it down to closer to an algebra level of math. Some of you guys might watch this video later and be like, Nasankala, you're ridiculous. This video was super easy to follow. But it was hard for me to follow, so I figured it might be easier for me to just like talk for a little bit and explain it the best way that I was able to understand it. But if you do decide to watch this video, at about the 5-minute point, it's going to talk about this logistic curve. Don't really worry about the vocabulary and everything, but it's going to tell you how we could check to see when we're getting closer to the level out point. Again, like I said, we're in the scary part of the graph now. That part of the graph will end. Okay, we're going to get to the flattening, and then we're going to get to the exponential decay. Okay, we're just in the growth phase. And I really liked the way the guy ended the video that I'm sending you guys. Is it was like kind of ended with like I think he said sufficiently worried, where it's like stay home and do the whole social distancing, but like it's gonna end. Like, this isn't the end of the world. It's just a phase, and this is just how we're gonna have to be for a little while, and then we're kind of making the sacrifice and deciding we'll be this way for a longer time so that we're able to treat everybody. So with that being said, I've officially gone until I have 5 minutes left. And I pretty much covered everything I wanted to. So what I'm going to do now is I'm going to go ahead and, once I figure out where my buttons are, I'm going to stop the recording so that we can actually like talk to each other like human beings instead of me just talking at nothing. So